This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is Thevenin's theorem as applied to DC circuits. Our objective is to learn to employ Thevenin's theorem in an effort to simplify complicated linear two-terminal networks into their Thevenin's equivalent circuits. Ideally, the original and the Thevenin's equivalent circuit will behave identical to each other. However, the Thevenin's equivalent circuit will be notably easier to build and to solve for desired electrical quantities. Bottom line up front. Thevenin's theorem is essential to your progressive development in the basic electronics series. It is a key rite of passage and will be regularly employed because it has the power to render even the most tangled and gnarly of series parallel circuits into tame and docile pure series circuits that sit, stay, and roll over on command. I will admit Thevenin's theorem is not exactly the easiest theorem to learn because it requires a degree of spatial awareness that may or may not be your strong point. In my experience, individuals struggling with Thevenin's theorem don't necessarily have issues with the electrical concepts, but rather they have issues visualizing a circuit from different perspectives. It is for this reason I typically start discussions on Thevenin's theorem with this seemingly simple question. What is the resistance of this 4-resistor circuit? Before you rush to judgment, be warned, I've given you no solid ground upon which to stand. Resistance is a two-point measurement. Which two terminals are we reading resistance from? If we read resistance from A to D, R2, R3, and R4 are clearly in series with one another, and this series path is in parallel with R1 for a total resistance of 153.4 ohms. If, however, we read resistance from B to C, R2, R1, and R4 are clearly in series with one another, and this series path is in parallel with R3 for a total resistance of 240.7 ohms. If we shift our terminals of interest yet again, from B to D, now R1 and R2 are in series with one another, as are R3 and R4, and these two series paths are in parallel with one another for a total resistance of 275.4 ohms. Numerous other combinations exist, each with its own total resistance value. The point is, resistance measurements of this seemingly simple circuit are like trying to nail jello to a tree if you consider different perspectives. This is the biggest stumbling block I've witnessed for students first learning Thevenin's theorem, and I'm asking you to keep this in mind when putting it to use. Observed electrical properties depend upon your perspective, and Thevenin's theorem shifts perspective from the source to the electrical load and back again. Throughout the course of the DC circuit analysis playlist, you'll notice that I've regularly drawn sources on the left and electrical loads on the right, only very rarely switching it up now and then. This isn't a necessary requirement, and the only reason I've regularly made use of this convention is out of sheer pity for those enrolled in basic electronics classes. Trust me, I've been there, and I was just as confused and frustrated as you when I first learned this material, back when the wild mullet still roamed the earth. My biggest complaint about textbooks isn't that they're expensive, heavy, static, poorly written, and hopelessly old school. It's that the example problems accompanying each chapter are so awfully convoluted and impractical that students just learning electrical properties are so shaken by the purposely goofy obfuscations they never learn the electrical theory the practice problem was intended to demonstrate. Hamlet doesn't just start out with some dude getting stabbed. A better approach might be to start easy and slowly turn up the heat. Not sure if you've noticed it or not, but if you've been following this lecture series in its intended order, I've been progressively turning up the heat. Sure, the illustrated example problems include general guidance, but think about it. I'm not holding your hand leading you through every step of a calculation, telling you which numbers to punch into your calculator, nor reminding you about engineering notation anymore. I say things like Ohm's law states this, and because this is in series with that, we can assume this, and so on, and just flash a number on the screen and move on. Not sure if you've ever looked down, but I pushed you out of the nest a long time ago. If you've reached this point in this series, it's because you're still flying. Let's turn the heat up another notch. See if you can solve for the voltage across, the current through, and the power dissipated by the variable load resistor R load when R load is set to 500 ohms for these 4 circuits. Again, we're only looking for the voltage across and the current through R load for each of these 4 circuits when R load is set to 500 ohms. By all means, pause the lecture and try this on your own. Do not sit there and wait me to guide you through this exercise. perform a Kirchhoff's current law and a Kirchhoff's voltage law analysis on these 4 circuits, and determine the voltage across and the current through and the power dissipated by the variable load resistor when our load equals 500 ohms. Yes, these circuits look a little different than the ones I normally give you. Don't panic. Trust the skills you have and put these skills to the test. If you're tracking, you should have obtained the following results. Those with a degree of spatial awareness should have realized that these were not 4 different circuits, but rather 4 different iterations of the same circuit. They were all purposely goofy obfuscations of a series parallel circuit in which a source, E, sees a 440 ohm resistor in series with a parallel combination of a 680 ohm resistor and our load presently set at 500 ohms. Let's use this particular configuration for the purposes of analyses, where a 30 volt source E sees R1, a 440 ohm resistor, in series with a parallel combination of R2, a 680 ohm resistor, and our load currently set at 500 ohms. An application of Kirchhoff's current law demonstrates that source current must flow through R1, then splits into 2 paths, one afforded through R2 and the other through our load. For all 4 implementations, it can be said that I source equals I1, which equals I2 plus I load. An application of Kirchhoff's voltage law for this loop in red demonstrates that E equals V1 plus V2. Similarly, another application of Kirchhoff's voltage law for this loop in orange demonstrates that E equals V1 plus V load. Finally, another application of Kirchhoff's voltage law for this loop in yellow demonstrates that V2 equals V load. These analyses imply that R2 is perfectly in parallel with R load, a simplification I'm calling R single prime, where R single prime has a value of 288.1 ohms. R single prime is perfectly in series with R1. An application of Kirchhoff's current law to the pure series simplification demonstrates that I source equals I1, which equals I single prime. An application of Kirchhoff's voltage law for the pure series simplification demonstrates that E equals V1 plus V double prime. An application of the voltage divider rule, solving for unknown voltage V single prime, demonstrates that V single prime is 11.9 volts. R single prime is a parallel combination of R2 and R load. Voltage across elements in parallel is the same. This implies that the voltage across the load is 11.9 volts. An application of Ohm's law demonstrates that I load equals 23.7 milliamperes. Finally, an application of the power equation demonstrates the power dissipated by the load is 281.9 milliwatts. Done. As these examples were intended to illustrate, in addition to a thorough understanding of Ohm's law, one must possess a degree of spatial awareness to consider oneself adept at circuit analysis. This is to suggest that circuit analysis, despite being rooted in math and science, is not just a technical discipline, but also an art form, and that the finer points cannot be taught, but only learned by oneself. I cannot teach you flexibility, visualization, and spatial awareness. You must teach you these skills. This being said, here are some reliable tools that will help you out. Kirchhoff's voltage law and Kirchhoff's current law. Never, ever attempt to analyze a circuit without first having performed a thorough Kirchhoff's voltage law and Kirchhoff's current law analysis. Application of fundamental series and parallel properties can assist you in visualizing how current flows through and how voltage is apportioned in a particular circuit, and allow powerful simplifications to be made. Rigid and recalcitrant individuals that refuse to use these techniques break apart. You cannot be reliant upon clear programmatic instructions because there are limitless possible configurations of circuits that can go wrong in limitless fashions. Now that we had a quick demonstration and discussion about visualization, let's dive into a discussion about electrical loads. Very often circuits are designed to deliver power to a variable load resistor, often designated R load, in this case presently set at 500 ohms. Oh crap. I've discovered an error in my illustrated example problems. Our load was meant to be a 200 ohm resistor. Sorry about that. Pause the lecture and recalculate all the values. Don't skip this step because it's vitally important to our later discussion. If you're tracking, you should obtain the following values when our load is set to 200 ohms. Wait a second, did I say 200 ohms? I meant our load was supposed to be an 800 ohm resistor. Sorry about that. Pause the lecture and recalculate the values. Again, don't skip this step because it's vitally important to our later discussion. If you're tracking, you should obtain the following values when our load is set to 800 ohms. Whoa, I do not know what is going on today. I am totally hosing up this lecture. Our load isn't supposed to be 800 ohms. I meant our load is supposed to be 880 ohms. You can see the mistake, can't you? Go off and calculate these values again. While you're at it, calculate these same values when our load is 8.8 ohms, 88 ohms, and 8,800 ohms. I'll wait for you. A long long time. Do you see the point I'm driving at? Every time our load changes, you change the whole circuit, and it necessitates another complete series parallel circuit analysis. This is a serious drag, and there has got to be a better way.